Hello everyone, my name is Aslan Mojallal and I am a senior power engineer and R&D manager at ETAP. Today we are going to discuss about power plant controller solution that we have here in ETAP. In today's energy landscape, the role of power plant controllers or PPCs is crucial. As a vital part of the SCADA and control solution, PPCs regulate and control inverters, energy storage systems, generators, capacitor banks, and the other equipments of a renewable power plant. PPCs ensure that plant behaves optimally at the point of interconnection, or POI, in terms of production levels, revenue, compliance, and grid stability. With the increasing penetration of renewable energy, the demand for reliable and accurate control systems has never been higher. Given the diverse designs of renewable plants, a flexible PPC solution is essential, particularly for hybrid plants. The ability to rigorously study and validate these systems prior to deployment adds immense value, ensuring PPCs meet the unique demands of each plant while supporting the broader goals of energy transition. The conventional technology for power plant controllers often relies on PLC-based solutions. These controllers are well suited for simple plants with basic control logics, offering reliability and ease of use in straightforward applications. However, as the complexity of renewable power plants increases, particularly with integration of hybrid systems, the limitations of PLC-based solutions become apparent. These solutions struggle to handle the sophisticated control requirements of hybrid plants, such as managing multiple points of interconnection or implementing advanced functions like virtual inertia and damping. This makes PLC-based systems less adaptable to the evolving needs of modern renewable energy projects. Therefore, customers in renewable energy sector are increasingly facing challenges with their power plant control systems. Many are working with PLC-based solutions which, while effective for simpler setups, are beginning to show limitations as plants become more complex. For example, customers often struggle with the integration of multiple types of generation assets such as wind, solar, and energy storage within a single cohesive control system. This is especially true for plants with multiple points of interconnection, where coordinated control between different zones is critical. Reliability is another major concern. Customers require solutions that they can trust to operate without fail, even under the most demanding conditions. This level of dependability often necessitates extensive pre-deployment studies, along with the robust hardware and software redundancy, which can be difficult to achieve with existing PLC-based systems. Finally, the customers are looking for solutions that simplify the complexity of a power plant controller. They want solutions that are not only powerful but also easy to deploy and configure, reducing both the time and costs associated with bringing a new plant online. The ability to rapidly adapt to new requirements is increasingly seen as essential, but this is something that traditional PLC-based solutions may not fully support. Our ETAP solution, the EPPC, sets a new standard in the power plant controllers by directly addressing the challenges that traditional PLC-based systems often face. At its core, EPPC is a software-based solution which allows it to execute complex and sophisticated logics that are crucial for modern power plants, particularly those with hybrid configurations. One of the key strengths of EPPC is its model-driven nature. This feature not only enables rapid and error-free deployment, but also ensures that the controller is perfectly aligned with the digital twin of the power plant. By integrating closely the ETAP's robust simulation environment, EPPC allows for thorough testing both in software in the loop and hardware in the loop configurations before any real world deployment. This level of testing and validation significantly enhances reliability and helps avoid costly errors once the system is live. Additionally, ETAP simulation software offers critical study types like grid code compliance studies and transient stability analysis, which complement EPC's capability and ensure that the entire system is well prepared for operational challenges. Reliability is further reinforced by ePPC support for both software and hardware redundancy. This means that in the event of an unexpected failure, the system remains operational, ensuring continuous control, which is vital for power plants where downtime is not an option. ePPC also excels in providing fast control response times, enabling quick and precise adjustment to shifting grid conditions. The inclusion of advanced functions such as frequency and voltage support is particularly important for maintaining grid stability, especially in the face of fluctuating renewable energy inputs. These capabilities further enhance the overall performance and reliability of the power plant, making ePPC a future-proof solution for renewable energy projects. Another key feature of the ePPC solution is its software-based nature, which supports agile development and allows it to be tailored to any specific power plant project. Being model-driven, ePPC significantly reduces human error throughout the entire process, from design to final deployment. This ensures that the solution is closely aligned with the power plant's digital twin, resulting in a more reliable and efficient performance. Our model-driven solution offers a seamless journey from the design of a power plant to its full-scale operation and control, all within the ETAP environment. It begins with the design phase, where every component in the plant, whether renewables, transformers, or capacitor banks, is meticulously modeled in the ETAP. This comprehensive modeling includes not just the physical attributes, but also the settings and operational capabilities of each element. Various ETAP modules, such as load flow, transient stability studies, are employed to accurately size the assets, ensuring that they meet the demands of the plant. Grid code studies are also conducted within ETAP at this stage to verify that the plant complies with all necessary regulations. Now let's take a look at how it works. The first step is to model the electrical system using ETAP's one-line diagram, or OLV. To do this, we must be in the base revision and in the edit mode. The software provides a wide variety of elements that may be present in your project. The level of detail in modeling each element can be adjusted to match your specific needs. Once the electrical model is complete, we can add primary controllers, POM meters, and gateway controller. This is a straightforward process. Each controllable generating unit requires a dedicated controller. For example, for each PV, we have one PV controller. The same goes for WTG and WTG controller, BESS and BESS controller, and so on and so forth. For each point of interconnection to the grid, you also need one POM ID, which is basically the meter that measures the active power, reactive power, voltage, and frequency at the point of interconnection and report it to the power plant controller. For example, in this project that we have 2 points of interconnection to the utility, we have 2 POM IDs. And finally, you always have a single gateway controller in your PPC models. ETAP offers several powerful tools to assist with modeling. For example, if you need to verify compliance with the grid code requirement, you can define these requirements in the rulebook. You can find rulebooks under rules in capability and control right through and different items that are available here. ETAP allows you to use a predefined rule or create custom ones. For example, this is an example of a rule book that we have for write-through capability for LVRT, HVRT, LFRT, HFRT. Or you can also specify the equipment capabilities that you have for your inverters and other assets that you have in your system. Here's another built-in example that is available in ETAP. But you can define your own capability and grid code requirements in the rulebook as well. Another valuable feature at this stage is the ability to add load and generation profiles. When using the time domain unbalanced load flow module or TDULF, the system generation and load can be followed according to a profile that you enter. You can also use the sectors that are available in ETAP. You can find them here under library, profile library, and you can select from a wide variety of profiles that are available here, or you can modify them according to your needs. Finally, for analyzing the behavior under fault conditions, you can use the transient stability or star Z module to simulate faults at different locations and study their impact on the system elements and see how your controllers behave and how your controllers respond to such an events. Once the model is built, the next step is to integrate the controllers, including our EPPC. Thanks to the model-driven nature of EPPC, this integration is smooth and automatic. When an element in the project is associated with EPPC, all its settings and connectivity are instantly transferred to the controller, making them available for the logic setup. This ensures that the controller is perfectly aligned with the rest of the plant's model. Now, once the system model is complete, we can integrate the EPPC, which is ETAP Power Plant Controller. This is done by selecting the controller element from the instrumentation section in the edit toolbar and placing it on the project. To load the controller logic, we need to open the controller, navigate to the DLL page, and click on the import button. This opens the ETAP folder where logic files are stored. Select EPPC, OTI controller, eppc.dll, and this loads all of the settings and logics for the PPC. Once the DLL is loaded, we must associate the relevant devices with EPPC. Navigate to the Associated Devices page and assign elements that EPPC will monitor and control. EPPC primarily interacts with the other controllers rather than directly with the generation assets. For example, it communicates with the PV controller, which then in turn control the PV elements. So PV controllers should be associated here. In our demonstration project, we have several PVs and WTGs, and accordingly, WTG and PV controllers, 2 battery energy storage systems, 2 STATCOMs, 2 POM meters, and 1 gateway. And all of these elements should be associated here in the PPC Associated Devices page. By associating these elements, their settings are automatically transferred to EPPC without manual input. This leverages ETAP's model-driven structure and feature, which helps a lot with the efficiency and ease of use. In the Associated Devices page of EPPC, we should enable Monitor if EPPC reads the measurement from a certain device, and we should enable Control checkbox if EPPC is supposed to send command to that device. These options are particularly important for hardware in the loop or HIL testing and field deployment, where toggling these settings affect IO DMP3 tag assignment. And with that, we basically integrate the EPPC model into our model. It's very straightforward. The next step is setting up the necessary logic in EPPC. An ETAP can be used to simulate and monitor the controller's behavior to ensure it functions as intended. This step is crucial for validating the system before deployment. When it's time to move from design to deployment, the logic can be easily uploaded to the EPPC hardware through a straightforward process in ETAP. Configuring the communication settings and deploying the logic takes just a few clicks, making the transition from the design to operation both efficient and error-free. Next, we need to configure the EPPC settings for the required functionality. As discussed previously, this can be done from the DLL page of EPPC Controller Editor. At the device level, we define some basic functionalities and settings of the PPC. For example, whether the controller is enabled or not, what is the execution rate of this controller, and whether we are running the simulation in the software environment or in the hardware in the loop. These settings do not define a certain functionality of ePPC, but a more general device level setting that is available. In the system setting, we define some of the more basic and system level settings of ePPC. For example, if our POM has a redundancy, it needs to be defined here. If we are using a specific rulebook for the capability of the entire plant, again, it needs to be defined here. And if our primary assets and our generating units are having any specific capability requirement, it can be defined in the system setting of ePPC. The general settings concern more about the general parameters of the plant. For example, what is the base value that we need to consider can be entered manually or calculated automatically by ePPC, how the PPC should behave in case there's a fault in the system, and if a device becomes undispatchable, how ePPC should handle that. Those kind of settings are defined under the general settings. Next, let's talk about the core functionalities of ePPC. First one is active power control. The active power control uses a PI controller to regulate active power at this point of interconnection. It also has a ramp rate limiter to control power changes at POM. It supports a dispatch priority setting for hybrid plants. This becomes very important in hybrid plants where you want to dispatch different assets with different priorities. And it can also implement a droop-based frequency support which adjusts the output power during grid frequency fluctuations. Next, we have reactive power control, which is similar to active power control in the sense that it uses a PI controller to regulate the power at the point of interconnection. It regulates one of the three variables at a time, the reactive power, power factor, or voltage. It also supports a droop-based QV scheme adjusting reactive power during voltage fluctuations, and also it has a ramp rate limiter to limit the rate of change of reactive power at the point of interconnection. Next, we have renewable smoothing, which dispatches battery energy storage systems or BESS to stabilize fluctuations in renewable generations. ePPC offers three methods to do so: moving average, Gaussian filter, and ETAP ramp rate limiter, which allows the user to choose the one that best matches their application. Finally, we have soft start and stop of the plant, which ensures a smooth startup and shutdown of the plant based on the command of the operator of the system that is originated from the HMI. It can automatically open or close breakers as needed based on the settings that the operator wants ePPC to do. And these are the core functionalities of ePPC that for any project the users need to set. During the operational phase, ETAP's SCADA solution is used to manage the plant. An HMI is developed based on the plant's model, with ETAP SCADA acquiring real-time data from various sources such as breakers and meters and displaying this information on the controller center's HMI. This data is also fed into ePPC, where the internal logic, controller settings, and commands from the operator or higher layer controller layer are processed. EPPC then generates the necessary commands, which are relayed back to SCADA and subsequently sent downstream to relevant assets. Simultaneously, the HMI displays the updated information, raises any alarm or notifications, and logs all transaction and data for future analysis. This integrated, model driven approach ensures that every step from design to operation is handled within a unified and highly reliable environment, reducing the potential for error and enhancing overall efficiency. The final step in our process is hardware in the loop or HIL testing, SCADA integration, and deployment. This step ensures that the control logic we developed in ETAP functions correctly when interacting with real-world systems. ETAP is capable of operating as a real-time simulator, which means that it can continuously exchange live measurement and control commands with the deployed EPPC hardware. This feature is particularly useful for validating system behavior before deployment in the field and allows us to test and fine-tune the control logic in a safe, simulation-involved environment. To enable HIL mode, we first need to change the simulation mode from normal to HIL test. This switches the simulation to real-world operation that ensures that data is processed and exchanged at the same rate it would be in a live system. Next, we need to configure DMP3 communication settings, specifying such details such as IP address and port number of the DMP3 server and other DMP3 communication protocol related settings. This allows ETAP to communicate with the external EPPC hardware and sends and receive real-time data as if it were connected to the actual power plant. Once the HIL setup is complete, we move on to deploying the control logic. This is done by navigating to the associated devices page and clicking on the deploy button. At this point, ETAP automatically generates a deployment file with a .ppc or .mgc extension. This file contains all the necessary logics and configuration for EPPC to operate as intended. Additionally, ETAP creates an Excel file that lists all the I/O assignments. This is crucial because it provides a structured overview of how the controller will interact with the various assets in the system, including which measurements it will monitor and which commands it will send to the field or the real-time simulator. After generating the deployment file, we need to upload it to EPPC hardware. There are two primary methods for doing this. The first method is using the web client, which provides a browser-based interface for managing and configuring the controller, the EPPC hardware, and uploading the logics to the box, to the hardware, and updating, restarting, and cleaning up the hardware. The second method is by using an application called ICE Explorer, which offers more advanced options for uploading, monitoring, and troubleshooting the control logic. These two methods are used to upload the logic and monitor how the controller EPPC hardware operates during the real time. Once the deployment is complete, the EPPC begins operating in real time. It establishes communication with the DMP3 server and continuously reads live measurement either from the SCADA or ETAP real-time simulator. Based on the control logic we defined, EPPC performs the necessary internal calculations and sends control commands back to the SCADA or directly to the power plant. At this stage, we have successfully closed the control loop. The EPPC is now actively managing plant operation, making real-time adjustments to optimize performance and ensure compliance with grid code requirements. Additionally, it communicates with both HMI and SCADA, which allows the operator to monitor and oversee system behavior in real time. Now let's dive into the built-in functions of the EPPC solution, which are designed to handle the complexities of modern power plants with precision and efficiency. These functions fall into three categories: active power and frequency control, reactive power and voltage control, and renewable smoothing by energy storage. First, let's talk about active power and frequency control. EPPC excels in managing active power and frequency through a sophisticated control loop. It ensures that renewable resources, generators, and energy storage systems are dispatched effectively to meet the set point of the plant's point of interconnection. This function not only tracks the set point, but also provides frequency support using a droop curve, which helps maintain system stability. Additionally, EPPC can implement virtual inertia and damping, which are crucial for stabilizing the grid. Ancillary features such as soft plant shutdowns are also included to enhance operational flexibility and safety. Next, we have reactive power and voltage control. In the reactive power and voltage control loop, EPPC manages various resources such as STATCOMs, capacitor banks, and renewables to regulate reactive power, power factor, and voltage at the point of measurement. This regulation is achieved through either uniform dispatch or a priority-based dispatch. The solution also supports droop-based voltage control, which helps stabilize the grid voltage. Importantly, EPPC considers the reactive power capabilities of each asset during dispatch, ensuring optimal performance and stability. The last built-in function is renewable smoothing by energy storage. To address the inherent fluctuations in renewable generation, EPPC utilizes energy storage systems to smooth out these variations. By dispatching energy storage systems in tandem with renewable assets, EPPC enhances the uniformity of combined generation, reducing fluctuations and ensuring a more stable and reliable energy output. Overall, these built-in functions of EPPC provide comprehensive control and optimization capabilities, making it a robust solution for managing the diverse and dynamic needs of modern power plants. When it comes to modeling hybrid power plants, ETAP offers a comprehensive and detailed suite of elements especially designed for such setups. ETAP includes extensive modeling capabilities for components such as wind turbine generators, photovoltaic arrays, inverters, generators, switch capacitor banks, and the STATCOM devices, and so on. Each of these elements can be configured according to their specific technical specification. For instance, settings like voltage levels, capacities, and operational parameters can be accurately inputted through ETAP's intuitive editor, library, and rulebook features. This allows for precise modeling that can greatly enhance the accuracy of various studies conducted within the platform. After integrating these elements into the model, primary controllers and the point of measurement or POM meter can be introduced. Primary controllers are essential as they manage the control of individual power sources. Their main role is to translate commands from secondary controllers like EPPC into actionable control signals for electrical components. For example, they might convert active or reactive power set points into inverter currents or exciter and governor control signals. ETAP also provides a unique controller for the POM meter, which is needed for collecting all necessary measurement at the point of interconnection. This data then is passed to EPPC, ensuring that it has real-time access to vital metrics needed to manage the power plant effectively. Once these controllers are integrated, the next step is to incorporate EPPC into the project. This involves associating the primary and meter controllers with the EPPC and granting it access to the settings and operational parameters of all relevant electrical components. At this stage, the system is nearly ready for simulation and software-in-the-loop testing. However, before initiating these tests, the settings within the EPPC need to be configured according to the specific requirements of the power plant project. This customization could involve setting up sequential dispatch for asset management in one project or configuring renewable smoothing function in another. The flexibility and depth of ETAP modeling capabilities makes it possible to tailor each project to its unique operational needs, ensuring that EPPC can perform its role with precision and efficiency. Let's walk through how to set up the simulation for EPPC. One of the primary tasks for EPPC is to track set points that typically originate from the system operator, often through the HMI in the control room. When working within ETAP simulation, particularly in versions prior to ETAP 2024, these set points were generated using a unique controller called the gateway. However, with the release of ETAP 2024, the process has been made more efficient. Now, the user can directly implement these commands as events within the event page of the time domain load flow or transient stability modules. This means you can easily schedule commands like active power, reactive power setpoints, or operational modes at specific times during the simulation. This approach not only simplifies the process, but also allows for more precise control and testing of how EPPC will respond to these commands during real-world operations. To prepare for deployment in the field, the final step is to deploy the logic and settings from EPPC and conduct hardware-in-the-loop testing. HIL testing requires a real-time simulator, which can be ETAP or another compatible simulator. Deploying the logic is straightforward. Simply click the Deploy button in the associated page of EPPC Editor. This section generates a package containing all the EPPC settings and logic. The logic can then be uploaded either through controller's web client or using a specialized ETAP application designed for this purpose. This application allows you to upload, manipulate, and monitor the real-time operation of both the controller hardware and the simulator. Once the deployment file is uploaded to the controller hardware, all necessary inputs and output tags are generated as DMP3 master, ready to interact with the ETAP simulator as the DMP3 server for the HIL testing. Once the HIL results are confirmed to be satisfactory, the hardware and logic can be shipped to the field for integration with the SCADA system. To conclude, let me recap the key aspects of our EPPC solution. Our advanced power plant controller stands out by addressing the limitations of traditional PLC-based systems with a modern software-based approach. This flexibility allows it to effectively manage complex hybrid power plants with multiple points of interconnection with seamless efficiency. One of the standout features of EPPC is its model-driven design. This solution not only accelerates deployment, but also minimizes human error by ensuring that every stage of development aligns precisely with the digital twin of the power plant. The ability to conduct comprehensive testing through software-in-the-loop and hardware-in-the-loop configurations further guarantees that the system performs optimally before real-world deployment. EPPC excels in delivering reliably through both software and hardware redundancy, ensuring continuous operation even in the face of unexpected failures. Additionally, it offers rapid control response times for advanced functions, which are essential for maintaining grid stability during fluctuating renewable energy inputs. The advantages of EPPC extend to its software-based nature, which supports agile development and customization for specific projects. Its model-driven approach ensures accurate and efficient performance by aligning closely with the power plant's digital twin. With its comprehensive capabilities, EPPC not only meets the complex demands of modern power plants, but also provides a future-proof solution for effective power management. Thank you for your attention.